Do you know that a little bit of automation can be done inside a spice deck? Do you know how you can define a global variable inside a spice deck? Do you know how you can alter multiple factors and run multiple set of simulation from a single spice deck? Stay tuned till the end of the video to know all the answers. Hey guys, welcome back. In today's episode, we are going to discuss the below points. First, we will talk about the alter concept along with the parameter concept, and we will learn how both are used together and how param can impact the dot alter. With the help of infographics, we will understand the whole scenario. Next, we will talk about the param, that is the parameter, as a global variable. We will talk in two directions. One, how it is impacting the alter, as well as how this global variable is impacting the spice as a whole. Next, we will talk about the param with various examples. In these various examples, we will understand how the parameters can be used efficiently to control any part of the spice deck. Next, we will talk about the impact areas where the alter can impact in the VLSI spice. Next, we will cover the coverage and limitation of the alter state. And at this point, we will conclude our today's episode. Before proceeding any further, I would like to mention one thing. In some of the simulator, it is used as dot alter. In ngSpice, it is used as a alter in the control section. You remember we have a control section at the end of the spice deck, which is exclusively for the ngSpice. So there we use the alter. And in multiple spice simulators, the dot alter is used as dot alter. That is why I am saying interchangeably as dot alter and alter, because in ngSpice you will find it in the control section of the spice deck. So the concept or the philosophy of the alter is same. However, syntactically it is used differently in different EDA vendor simulators. So you must be prepared so that whatever you learn here, theoretically that will be same for all the simulator. However, syntactically there will be some change from one EDA vendor to another EDA vendor. So without any further delay, let's begin. This part today which we are discussing is broadly categorized as the simulation control. That means how we control the simulation. Here in this slide, we will talk about the concept. That means the philosophy of alter and the parameter, how they can be used together in VLSI spice. Before going any further, I would like to show one thing here. Say you have a spice deck here and you have some statement here. For multiple cases, you need to change this statement and rerun the spice deck. So that will be very cumbersome. That means every time you have to manually change this statement, then rerun, store all the output results, and then you have to go again, change here and run. And in this process of storing, you have to make sure you keep it in some folder, right? So there you have to do it manually. So this is a very cumbersome process. Now, if there is a mechanism by which you can automatically reset all the changeable values of this particular statement, and automatically different nomenclature will be created for different set of values, right? All those data rather than databases will be created with different nomenclature. That will be a good thing for a VLSI spice engineer or VLSI analog design engineer. Now, this feature is alter. Again, I am saying interchangeably, this could be a dot alter as well as this could be a alter. Now, let us see with the infographics how this is done. Here is your spice deck, which you have written in your analog design. Now, simulation will run with the primary setup. That means whatever you have written here, right? All the statements, right? Here you have written, all those will run with the primary setup. Now, when the alter comes into the picture, first change, which you have already included using the alter, what will happen? The simulation will rerun with the altered parameter. Here comes the word parameter, and that's why we are using the dot param. However, you will see this alter philosophy is not only limited to the parameter, but it is extended to many other features of spice. Again, we have the second set of values with which we want to run, that is with the alter 2. And what will happen? The simulation will rerun with the entire process with the altered parameter. So we have some value here and we have some value here. This is some value here and this is some value here. So these two are different values and the spice will run. So this is a very small and simple infographics to understand. However, this change could be numerous. Say 10, 20 changes are there. So in those cases, the entire simulation will be run, and as a result, whatever the output database is coming, right, that database will be renamed accordingly, and then all those databases will be saved. And there is another fact: you don't have to run manually again and again by hand. Rather than you set all these parameters here in the spice deck, whatever the list of values will be used in the multiple alter statement, and they will run automatically. And at the end, it will finish and you will have separate databases for all the altered parameters. Why this is important in VLSI? In VLSI, sometimes we need to change some of the values to see what is the figure of merit is coming out of that particular parameter. Why the figure of merit is important? Because when you are doing an analog design, your design will have some characteristics like frequency, voltage, etc., right? Gain, anything could be there. Now, these figure of merits can be impacted with set of change in the input. Now, this figure of merits can get changed with some change in the input parameters. Now, you have to decide which parameter is impacting in which way, so that when you create a proper documentation on the figure of merit of your analog design, whether it is a block level design or it's an analog IP, that time you have to be cautious that these factors can impact. So as a designer or as a verification engineer, analog verification engineer, this has to be in your mind, so that you have this picture that okay, these points can impact the design output or the design performance. Now here you have the option to tweak the inputs, not the test vectors. First of all, here we are not changing the test vectors. The test vectors, that means whatever input signals are going into the analog design, we are not changing that. We are changing different internal parameters of the circuit design. And that is how we judge that the figure of merit of that particular design, how it is getting impacted. And that's how we list down all the values, and finally we create a documentation of the figure of merit. This is the purpose in VLSI of using the alter philosophy along with the param. And again I am saying the alter philosophy do not only work with the dot param or the parameter, it also works with many other factors which you will learn in this video only. Here we are done with the infographics. Let's move on to the next slide. Param, the global variable. Now let us see the parameter, how we can use as a global variable. You know about the global variable, local variable from the programming language like Perl, Python, Tcl. You already know. We have all these series in our channel. So you know about the global variable concept. Now in Spice, how this we can introduce? We can introduce this global variable concept with the help of param or parameter. The param is a shorthand of the word parameter. So let's learn about this parameter. First, the syntax is like that: param, then parameter name 1 and its value 1, then parameter name 2, value 2. All these are space separated. So here we have a space, and again we can give a space and we can write here parameter 3 equal to value 3. So this way we can continue and we can write multiple parameters in a single statement. Sometimes in VLSI we do what? We write separate statements, because this parameter could be one category, another set of parameter can come from another category. So we do the separate categorization by separate dot param statement. That is a convention that we can use while we are writing the spice deck in VLSI. It sets the global values. That means whatever you set as a parameter, right, that can be used anywhere inside the entire spice deck, right? So that's why it is the global value, or it is the global variable similar to the programming language like Perl, Python, etc. Parameterize input element towards model data. So this is the flexibility of the parameter concept or the parameter philosophy, that we can extend it up to different input element, different input source and model data. we can use it in multiple ways. So it's a kind of Swiss Army knife that can be used not only as a global variable but also as to parameterize different input elements of the spice deck. Algebraically manipulate output, print or plot variables. That is another utility central to circuit optimization and multiple simulation runs. So this parameter, as I said, the parameter has a deep connection with the ALTER philosophy or the ALTER statement, and that is used for multiple simulation runs. Let us see some examples here. First, here we write the parameter WP is equal to 50 micro, LP equal to 0.6 micro, LN equal to 0.6 micro, ABC equal to 10. You can see these are in bold. So upcoming lines will have all these parameters and they will be in bold. So watch out for the upcoming lines. Here we have a inverter, right? The instance is x1 and we have here its different values of its parameters. However, we are not using the param here. That means we are not using the values here. However, in next step, we will see. Here we have the dot subcircuit and we have the set of input outputs, or the subcircuit name is here, and we have all the parameters. Now, inside that, when we write a MOSFET, right, we use these global values. You can see WP is coming here. So this value is coming here. L is equal to LP. So LP coming here. And M is equal to ABC. So ABC 10 value is coming here. Although these are individually defined, so they are not impacted. But however, here, these values are impacting here. Next, we have another MOSFET, that is the N MOSFET. We have W equal to WN. So although we do not have defined WN here, we should have defined the WN equal to something here, and that value would come here. LN is coming here and M is equal to, here there is a typo, CBA, it will be something here. We write CBA here, another parameter, and that should come here. So this way we use the global values in the spice deck anywhere, and these values can be used in a multiple ways. And what we are standardizing here, if you look carefully, we are standardizing the MOSFET size and etc, the MOSFET parameters that we are using throughout the entire design. This way we are making sure that we are using the same size MOSFETs throughout the design. So we can have multiple sub-circuit definition inside one particular spice deck in VLSI analog design. So there, this way we are standardizing. That means we are defining here and we are using it throughout. Next, we end the subset. So you can see how the parameter can be used as a global variable, which is very similar concept to the global variable from the programming language like Perl, Python, SQL, etc. This way we can use the param as a global variable. We are done with this slide and let us move on to the next slide. We have seen one particular use of parameter concept as a global variable in the last slide. We have seen one particular use of parameter as a global variable in the last slide. Now in this slide, we will see some more various kinds of example. So here we signify various colors here to see various examples. Now let us start. Defining your own functions. Param can be used to define functions. These are inline functions. How? Let us see. So dot param, then we give a function name, then we give argument 1, argument 2, and then we have the parameter expression. So this is a generic way. These are very simple thing that we can calculate. Example, we have gain, then we have out, then in, and we have V out by V in. So this is the function that will calculate V out by V in, and this will give a gain. Next, we have print statement. Inside that we are using this. We are using this particular gain print. We are printing the parameter, right? And we are using the gain, right? And again we are writing my gain is equal to parameter, then again gain 31. So this way we can use it. Now we define parameter raise equal to 10k. That means 10 kilo ohms. Then we can write parameter t time is equal to 12,000 m, that is millisecond. Then we write parameter v area is 100. Next we write t time 10 is equal to t time by v area. So this way we can go on define parameters and we can use a previously defined parameter like this in the next parameter as an expression, right? Next, we can use it for random control of voltage Gaussian distribution. This is a randomization. So here you can see our voltage, DC voltage is defined, and we are using a predefined function, that is T random, and here we are using T time 10. So T time 10, this one is getting used here to generate a random voltage value. Behavioral resistor. So this resistor is not a flat resistor. This has some functionality, and that functionality is defined by the parameter. Now you can see that resistance this between two nodes, and R is defined by this expression res. You can see res is coming from here, and we have some expression 0.033. So you can see in this expression the res is coming from here. Plus we have some fixed numerical values multiplied by res, which is again coming from here, and then VR. So VR2 is coming from a particular node. So this way we can have behavioral resistor, which is not a simple but some equation based resistor. These are some wide example of the parameter that can be used in the SPICE deck. We're done here with this particular slide. Let's move on to the next slide. So in this particular slide, we will talk about alter, and we will talk about different areas where the alter can impact. First, the entire simulation runs with the primary or initial setup, and then the alter block causes rerun a simulation several times with different alteration in the wide spectrum of things. Now this wide spectrum of things are listed down. Let's see the list. First is the circuit topology. Next one is the models. Next one is the library components. We know already about the SPICE sleep, and they can be changed with the alter philosophy. Next, we have the elements. Circuit elements also can get altered by the alter philosophy. Next, we have parameter values, which already we have came across. Next, we have different options for the settings and etc that we already know from previous episodes, or something which we may come across upcoming episodes. Next, we have source stimulus. Next, we have analysis variables, and we have print or plot commands must be parameterized. That means there should be a parameter included either in the print or the plot command. So all these wide spectrum of things can be impacted. That means can be altered with the alter philosophy. And this is the overall introduction to the alter philosophy along with the parameters. Once you go deep down the analog designs in VLSI, you will come across all of these things one by one and in case by case basis. We are done with this particular slide. Let's move on to the next slide. Here in this slide, we will talk about the coverage and the limitation of the alter philosophy. Now, first, the alter can include. Now we are going in a very explicit manner what the things can be there in the alter. Previous slide, we have talked philosophically or as an overview. Now here we will go in an explicit manner. Element statements except source, dot data, dot lib, lib. These two has to be used in coupling or in sequence to activate or deactivate one library, then inclusion of the next library. Next, we have the include. We include some file, dot model statements, etc. Next, we have the dot IC, dot not set statements, which already we have discussed in last episode. Next, we have the dot OP, the dot options. Parameter we have already talked about in this episode. Dot temperature, that is the temperature of the entire simulation. TS, PRAN, DC, AC, etc. So all these things we can include inside the alter philosophy. That means we can use these along with the alter philosophy, whether it is a dot alter command or alter philosophy in the control section of the simulator. Now we will talk about which we cannot include. Here is a fencing. Fencing means you are barred to use them. We cannot use print, plot, grass, any other IO statements. We talked about that we can use parameterized ones, but the simple ones we cannot use. Avoid adding analysis statements under each alter block. Analysis means we do the transient, AC, DC, all this type of analysis. That should be avoided. The analysis will remain same. However, we can include all this type of things inside the alter philosophy. And we cannot include this type of thing until or unless they are parameterized. So here we are done in a very short and sweet manner. So let's move on to the next slide. Thank you very much for watching up to this point, and don't forget to like, share and subscribe. In case you have some dislikes, put that as in words in the comment section down below, and bye for today.